Hello, everybody. My name is Dr. Reza Azardiraksh, and I am Associate Professor at Florida Atlantic University. Today, I would like to talk about post-quantum cryptography, and I would like to focus on super singular isogeny key encapsulation. So, as you may know, quantum computers, and basically large-scale quantum computers, will be able to break our current cryptographic protocols that we use today. So assuming that quantum computers will be available by 2035 or 2030, in a decade, let's say, we need to take action now and switch our current cryptographic protocols to something which is called post-quantum cryptography. For instance, elliptic curve cryptography and RSA are mainly cryptographic protocols that they need to be migrated to quantum safe alternates. So NIST started, National Institute of Standardization and Technology started in 2016 to look into the candidates and algorithms that could stay secure at the time that there are quantum computers. And in 2017, they started round one. They accepted round one candidates to study them in terms of the security problems and also studying the quantum security problems. By 2019, they started accepting and looking into narrowing down the candidates to just 26 candidates, including signatures and digital signatures. And recently, by August 2020, NIST announced round 3 candidates. They will stay there for a year and a half, almost 18 months. And by 2022, NIST will standardize some kind of quantum safe key exchange and digital signature algorithm. So basically, what we would like to address and talk about that today is that we would like the community to be aware that first, attackers now can download encrypted data any days 2016 until 2030 or 35 that quantum computers will become available, and they can decrypt the data, retroactively get access to our private data. And the other problem is that migration to new crypto systems usually takes years or sometimes decades, because in the past we've seen that even the migration to RSA always takes forever and it's not been completed yet. So basically, we need to take action if we would like to be secure against the attack of quantum computers because of those two reasons, and we need to be provide solutions for our protocols that they use, for example, RSA and ACC. So luckily, there are some key exchange candidates and digital signature candidates, as you could see from this slide. We have lattice-based, code-based, and isogeny-based candidates. So for signature also, we have lattice-based, hash-based signatures, multivariate, and zero-knowledge-based. So in this talk, I would like to focus on isogeny-based cryptography. And as you may know, lattice-based cryptography and code-based cryptography are also popular. They stayed in the round 3 as well as finalist. Isogeny-based cryptography is an alternate round 3 candidate. Hopefully it's going to be promoted to round 4, and after that it's gonna be also standardized. But no matter what, isogeny-based cryptography offers a special property that none of these candidates are offering, being providing smallest key size, public key size, which is very attractive for IoT devices. So I'm not going to talk about the digital signatures. The focus will be on key exchange and with the main focus on isogeny-based cryptography. So open questions for quantum safe basically are coming from designing better quantum safe crypto processors or crypto systems. We need to improve classical and quantum attacks. to study what's happening, what's going on with the cryptanalysis activities. We need to provide the data for people who are implementing to make sure in terms of parameter size and also selecting various parameters for their security levels. And also we need to develop fast and efficient implementations, also secure against like basic physical and other attacks. So finally, we need to integrate them into existing infrastructure, because that's also very important part of agile migration. SIKE team is basically composed of a couple of University of Waterloo, Florida Atlantic University, University of Toronto, and several big companies like Microsoft Research, Amazon, NXP, LinkedIn, Texas Instrument, IBM Research, and some startup companies, IF, Info Global, PQ Secure Technologies, and EvolutionQ. So the SIKE has a very strong industry and academia, and we hope that it will stay, get standardized and will be adopted by industry. So architectures wise, I would like to give an idea of what's going on with the implementations these days for crypto processors. So crypto processors basically could be implemented using hardware only mechanism or software only. You know that in hardware only we get performance boost, security. With software only we get a lot of flexibility and also like a little bit of help with the less complicated and complex designs that offers by hardware security, hardware only design. In between hardware and software design basically is a solution that you offload computations that are costly to a hardware, and sometimes you can keep the key in the CPU and host processor, or you can offload it even outside if you would like to make sure you have more security. FPGA's field programmable gate arrays are great because application-specific integrated circuit ASIC designs are costly and timely. So you can use FPGAs, various FPGAs are available for prototype of quantum-safe candidates and compare them with each other to get an idea of what's happening. So in comparison to ASIC, FPGAs are offering flexibility, reusability, short time to market. And what is important for us is to understand that compare like trade-offs between security, performance, and silicon area. And things are important like energy, power for small and embedded devices, or time to design. Sometimes engineering work is also important to understand, which sometimes adds a lot of cost. So, and when the design is completed, for example, in terms of FPGA, it could go to ASIC, or sometimes it could stay with FPGA implementation, say, for example, for IIoT, industrial IoTs, or car-to-car communications, because FPGAs are offering these days very competitive technology in terms of nanometer. For example, you can have FPGAs in possibly 7 nanometer, a lot faster than access to ASICs of same technology, right? So back to isogeny-based cryptography. If you remember, elliptic curve cryptography that in the left picture, as you could see, is based on an operation which is called point addition. Basically, if you remember Alice and Bob, they both choose a point on the same curve. Alice computes her own public key. Bob computes his own public key by multiplying their secret into the point on the same shared elliptic curve, and end up getting another point which is on the same curve. Here in isogeny-based cryptography, we are working on a set of elliptic curves. Basically, if we have an elliptic curves, we can map the elliptic curve to another elliptic curve, which is also called isogeny. So this hard problem in elliptic curve cryptography is that if you know the scalar or private, if you know the point on the elliptic curve and you know the public key of Alice, it is very hard to find the scalar that Alice multiplied point and she received the public key. Okay. which is called elliptic curve discrete log problem. Here problem is different, so we can have an image of an elliptic curve to another curve, and knowing the curve itself and the image of the curve, it's hard even for quantum computer to find the isogeny. So E prime is the image and phi is the isogeny function which you apply on E, you get E prime. So finding phi is the hard problem that we will focus here. So to better understand, I would like to give you an idea of what's happening with key exchange between Alice and Bob. Okay, so assuming that Alice, we would like to do key exchange for here, the Alice and Bob. So we want to get a setting for elliptic curve for isogeny graphs. So basically we need to lay down our prime, because we are working on, first of all, super singular elliptic curves over fp squared, rather than an elliptic curves that we are working on elliptic curve cryptography, we work on fp. So, for example, the form of the prime is p equal to 2 to the power ea times 3 to the power eb times the constant f minus plus 1. So, for example, if I choose my p to be like 71, I can write it down 2 to the power 3 times 3 to the power 2 minus 1. So, and that's 2 and 3 are 2 isogeny and 3 isogenies, and the exponent 3 and 2 are the walks that Alice and Bob will take on the graph. So if you look at this, my prime is 71, is a small prime. It's not good for cryptography, but it's good for my example, as a toy example. So number of points on this elliptic curve is basically p plus 1 squared, because I have super singular isogeny, super singular curves. It's going to be 71 plus 2 plus 1 squared. So, and that's the number of elliptic curves on this, number of points on this elliptic curve, super singular elliptic curve. Number of J invariants, number of isomorphism classes of this curve will be sp squared, which is kind of equal to p over 12. For example, p is 71 divided by 12, and then you get fluid, you get 7. And you could see here that I have 7 different J invariants. So for example, 0, 40, 17, 41, 48, 24, 66. So J invariant is a special property of elliptic curve that defines isomorphism classes. Okay, elliptic curves in the same isomorphism class, they share same J invariant, which is very useful for the discussion that I'm going to have here. So now we would like to work on isogeny graph. So Alice and Bob, they both are working on the same graph, as you could see from the previous, and we would like to connect these graphs. So nodes of each graph is isogeny of degree L. Okay, that we are connecting these links or edges that we are connecting these J invariant together. They're isogeny L. So I get with isogeny 0, I go to isogeny. I can go from J invariant 0 to J invariant 40. I can go to another isomorphism class. Okay, and vertices are all isogenous elliptic curves over fp squared. Okay, and that's curves that are inside the same J invariant or isomorphism class are called isogenous elliptic curves. So we assume that Alice is doing a 2 isogeny has an 2 isogeny graph connected. Bob has 3 isogeny graph. Okay, and then if isogeny graph degree is L, the graph is connected L plus 1. For example, if you isogeny 2 isogeny graph is connected by L plus 1. Okay, so now I would like to start the setting of algorithm see how a key exchange could have happened here for Alice and Bob together to get an idea of how to share the secret key. So basically we are working on an base elliptic curve E0 over FP squared. Alice chooses 2 points on the elliptic curve. Bob chooses also 2 points on the elliptic curve. Elliptic curve is in Montgomery form. Base elliptic curve E0 is x cubed plus x. Okay, and those are the 2 points for Alice, 2 points for Bob. So these are public parameters. They're available for everybody. Attackers can get access. They're supposed to be available as standardized documents or certificate authorities that people would like to generate keys. So there are also secret keys Alice and Bob should choose. And for example, Alice chooses secret SA equal to 6. Bob chooses SP equal to 3. Okay, so there are some conditions for choosing them, but and they should be inside these 0 up to 2 to the power EA and 0 to up to 3 to the power EB. Obviously, you don't want to choose 0, right? So starting from E0, a base elliptic curve for both Alice and Bob. As you could see, graphs are same exactly. They're connected differently because Alice is 2 isogeny, Bob is 3 isogeny, right? As you could see, nodes are the same. They're differently connected to each other. So Alice, starting base point E0, Alice and their J invariant of E0 that I have here is a Montgomery curve, y squared x cube plus x over my prime. Actually, don't forget that this is all over prime field over P equal to 71, which is 2 to the power 3 times 3 to the power 2 minus 1, right? So first slide. As you could see here, Alice maps E0 to EA. Look at this. When Alice maps E0 to another elliptic curve, which is, we call it Alice's curve now, or image of E0, Alice moves from 24, which is isomorphism class, or J with G invariant of 24. She walks 1 on herself, stays there, and then walks to 17, and then 40. So Alice walks 3. Alice takes 3 walks on isogeny graph. On the second side, in the right side, Bob takes only 2 walks, because Bob stays from 24, gets to 48, and then 17, right? So, and then we say Bob gets 2 walks, Alice gets 3 walks. So it's like 2 to the power 3 times 3 to the power 2. So again, Alice's graph is 2 isogeny graph, Bob's graph is 3 isogeny, okay? After that, they get EA and EB. So EA for Alice has J invariant 40, EB for Bob has J invariant 17. Okay, so and now they have to exchange their public key. What is a public key here? The public key is basically EA and the 2 auxiliary points. So remember, I told you that you can map an elliptic curve to another elliptic curve, or you can get an image of elliptic curve. You can also do the same, and you get like points. You can map 2 points. So Alice maps 2 points that Bob choose on the elliptic curves into another points, and that's got phi A of PB. You see that Alice computes image of PB and QB and sends it to Bob. Let's look at that exchange. So, and you're now working on different curves. EA is starting from 40 and EB was 17. So after we exchange, so what's gonna happen? Then Alice has to start from 17 and Bob has to start from 40, right? We did some kind of key exchange here, which is for public key, and they have to switch starting from another curve. So Alice will start from 40. Alice gotta do another 3 walks on the graph. Bob is supposed to do only 2 walks on the graph. We basically are repeating what's happening up there. By the way, the map that we do is based on a kernel. So when Alice maps E0 to EA, Alice computes first kernel of phi A which she has 2 points on the elliptic curve, performs a double point multiplication or ladder, and multiplies with her private key, gets the kernel. After kernel, she maps E0 to EA using Velo's formula. I'll get back on that soon. So doing the same thing from 4D, Alice starts from 17 and Bob starts from 40. As you could see, the colors are changed, also the colors here. So from 17, the Alice walks 3 isogenies, 17 goes 41, goes to 66 and comes back 41. Okay, on the right side, Bob does the same. Bob starts from 40, which he got from Alice, and does 2 walks on the graph only. So 2 walks will be 40 goes to 66, another walk from 66 to 41. Right? As you could see here now, they both ended up getting to another curve, which is EAB for Alice and EBA for Bob. And here, the isogeny graph, both Alice and Bob, they landed into an isomorphism class that share same J invariant, and they can use it as the shared secret. Okay, this is the whole idea of SIDH, basically, super singular isogeny Diffie-Hellman. So soon we will describe that how we basically perform the SIKE, which is a little bit more complicated than what you see here. Okay, so looking into parameter size for NIST level, NIST security levels, that example was super small and easy toy example. We were working with prime of size 71, p equal to 71. Here we are working with p of something like 2 to the power of 216 times 3 to the power of 137 minus 1. Okay, so and that gives you which is something like 434. So basically 2 to the power 216 and 3 to the power 137, they're like a similar size. And the public key size, which composed of 3 parameters that we are sending from Alice to Bob or Bob to Alice, is something about 330 bytes, and compressed public key size could be something about 196. So this is for NIST level 1. We increase those prime sizes to achieve higher security levels, which is very attractive for SIKE. You just increase the prime size and then you jump into next security level. So if I compare these, p equal to 71 basically is the graph has only 7 nodes. P equal to 2521 has 210 nodes. If I look into like 443-bit prime of big number there, number of nodes will be 2 to the power of 430 almost nodes. That is basically very difficult to simulate even. So which indicates the security basically of the system. Looking from the computation, if you remember, we are supposed to compute like a key exchange protocol, SIKE, SIDH, and other protocol signatures on top could be. And for that, basically, you perform from top to the bottom. Basically, you perform double point multiplication. You do large degree isogeny computations of mapping curve to another image of curve. If you go group operations, you perform point addition and point doubling, isogeny evaluations and computations. And the very on the bottom level, you get like FP squared arithmetic, and finally FP, which is finite base, finite field operations, addition, multiplication, and inversion. So if I would like to explain how we map an elliptic curve to another elliptic curve using Velo's formula, basically the answer is that we use a pyramid that you could see here, because large degree isogenies are difficult and computationally intensive. Instead of performing one large degree isogeny, we do small, we break it down into small degree isogenies, as you could see here. For example, phi, instead of performing phi 7, we do phi 6, 5, 4, 3, 2, 1, and 0. So that makes the computations a little bit faster for us. So so for basic thing is that we start from R0, which is kernel for E0 base elliptic curve, which is Montgomery curve, for example. We need to find out and order of R0 is basically L to the power E or L to the power 7. For example, for Alice, we would like to map E to EA, right? For Bob, we would like to map E to EB, and we need to calculate our 0 or RA. If we get order L of R0, that will be easy to find phi 0 and then map R0 to R1. Okay, then on this pyramid, as you could see on the left side, we do multiplications, we multiply by L. On the right side, we do apply L isogenies. Okay, we multiply R0 basically by something, we get a point of order or kernel of order L, and then perform isogeny. Okay, and these are basic steps are explained here. I would like to show that with an animation that I have here in my slides. So assume that we are working to push E0 to E6, and we have E equal to 7. Order of R0 is L to the power 7, and basically let's see what's going to happen. Basically, starting from E0, and we calculate R0. R0 is the kernel of E0. So where is it coming from? 2 points on elliptic curve, secret points, you do a ladder, you get R0. R0 has order of L6. You multiply order L7, L to the power 7. You multiply with L, you get order of L6. You multiply another time, you get L5. You keep multiplying until you get order of L. So order of R0 now is L. So as soon as I found this, I can go to another, I can map now E0 or R0 to R1, right? So, and I found on the bottom of this pyramid, I can find the other point, other node, which is using phi 0. Basically, that will give me L to the power 5 R1. So basically, I can do exactly same as in the left side, but I would like to avoid computing all those yellow lines because I would like to save and make my computations faster. I keep doing this until I reach, I compute all the bottom nodes, and then I reach the E0, E1, E2, E3, E4, and E5 and E6. So basically, that Alice, for example, is doing to get to map E0 to basically, and at the end, basically to E7, right? So you can do the same in the right side, left side one. That will be more more in computational stuff will be needed. Computations will be needed to determine E7. On the right side is more is cheaper. Remember, on Alice, for example, on the P NIST level 1, we need to perform 2 to the power of 236 VOX, and you're mapping E0 to E236, and the graph will be very big, right? So the pyramid will be super big. That Alice and Bob, they're supposed to do the same on the Alice and Bob side. So how you do actually the small degree L isogeny? L isogeny is using Velo's formula. The equation is available, and that's super easy and very fast computations you need to perform there to map. Just the most important thing is to get the low L degree L order L of kernel of the isogeny or kernel of the curve. Looking into the computations, I put together things into a box. As you could see, we have like if we are implementing such computations into in hardware, basically Alice we have a base point E0, we have 2 points for Alice PA QA, we have 2 points for Bob PB QB. We store them in memory, push them into ALU, we get compute, map E0 to EA, and the output of the algorithm, as you could see, a box is EA. And also we map these 2 points PA and QA to phi A PB, phi A QB, right? So because Alice is supposed to perform image of Bob's points, and Bob does Alice over Alice's points. In round 2, they exchange, they send EA to Bob and EB plus auxiliary points, and we get J invariant of E and B. So secret keys are could be generated using TRNG or QRNG, anything you feel comfortable working with. And ALU, the computations could be done using low field level arithmetic computations. So the kernel of isogeny that I just explained is very easy to compute. It's just only point ladder. You get a point, 2 points on a base point, and you perform PA plus SA times QA. Sorry, that should be multiplication by QA. And this is a 3-point ladder. Output will be RA, and RA is basically we multiply with L's. We get order L of RA, and then you map EA to E0 to EA over subgroup of elliptic curve points RA. So this is got isogeny computation. This is done using Velo's formula. And finally, at the output, you get EA, phi A of PB, phi A of QB. The most important computation for isogeny-based cryptography is the multiplication. So, and since we are working on Montgomery elliptic curves, this is very important to understand that the format of primes that we are working here are 2 to the power 3 or 2 to the power EA times 3 to the power EB minus 1. And as you could see, if you multiply any number with 2 to the power of 2's minus 1, you get all 1's, right? For example, 2 to the power 3 minus 1 is going to be 7, 1, 1, 1, 1, right? So multiplication adds them around your number in the bit representation. And if you do that, Montgomery representation will be even easier. So because P prime will be always 1, mod 2 to the power 3, which is W, is always less than EA of your isogeny Vox, makes Montgomery multiplication and reduction a lot better than other methods, for example, Barrett reduction. Okay, so there are many methods of performing multiplication. I encourage people to look into these more. CIOS, coarsely integrated operand scanning, and finely integrated operator scanning, or FIOS. They have advantages and disadvantages. In hardware, we figured out that CIOS sometimes could outperform FIOS. In software, it could be different. It depends to smaller devices if you're performing things differently there. Okay, so looking into the architecture, we get processing elements, we perform things systolically to achieve highest clock frequency possible. For example, here for FIOS design to make things faster. If you look into, if you are performing FP squared computations, basically I'm going a little bit another level up to my pyramid. The computations in FP2 could be breakdown into FP computations. For example, addition in FP2 is 2 addition in FP. Subtraction is basically the same, and multiplication follows Karatsuba rule. For example, the 1 multiplication in FP squared is like 3 multiplication in FP and plus 5 additions, and so on. So squaring is the same. Inversion, you can find them as well. So looking into SIKE, SIKE is the main algorithm submitted to NIST for standardization. It stays in the round 3 currently as an alternate candidate. Hopefully it's going to be standardized, and that's what I'm going to explain now. First, we need to have some public parameters, values for Alice, and some values and numbers for Bob. Okay, so key generation is the main thing. So basically Bob generates his public key using those public parameters available. So Bob has his own private key SB. Bob can map E0, which is our base point, to EB, and with just as you could see, kernel PB plus SB multiplied by QB, and then Bob publishes his public key. Public key is PKB, composed of an elliptic curve and two auxiliary points on the same curve. Key encapsulation is what Alice does. Alice basically encapsulates and Bob does decapsulation. Okay, so let's look into that, see how it works. Alice chooses a message and then uses Bob's public key. Bob generated the public key, it's available. Alice's public keys also will be available now during this encapsulation. So Bob's public key is used here. Alice makes a hash function or kechek, for example, is SHA-3 algorithm, variant of SHA-3, performs kechek of M and PKB. Okay, so PKB and M will be hashed, and that's gonna be R, which is kind of a secret key for Alice. And Alice will perform isogeny, will map the base point to get his curve, her curve EA. So as you could see, E0 now mapped to EA, and Alice can publish her own public key. So now Alice's public key is available here. In the bottom of this line, you can see that Alice also could perform to get EAB, because Alice has EB already received through public key of Bob, and Alice gets EAB with that R that's computed, and she gets also a kechek of J invariant of EAB and XORs it with a message M, and again makes we call it ciphertext, which includes the public key of Alice, C, which is hash of J invariant and the message, and publishes that after hashing one more time, which is called kechek of M, PKA, and C. And we will Alice will use this for as the shared secret key to decrypt whatever is coming from whatever she is sending to Bob. So we would like to see if Bob can decapsulate and get same thing. So Bob will perform the decapsulation. The ciphertext, which is SSA or CT, is coming. CT basically is coming to Bob. Bob perform EBA. Bob has his own EB and he maps EB to EBA. Right? That's and using his own secret key. So for simplicity, I didn't show that but SB is the private key for Bob, or secret key, sorry, for Bob. And Bob also gets a message M prime here, makes a kechek of J invariant. So Bob calculates the message, which is called M prime, which is part of E J invariant of BA plus XORed by C. The C is coming from actually Alice encapsulation, right? So and after that, so Bob also gets R prime, which is kechek of M prime and public key of Bob, which already he already has that, and then perform isogeny, gets A prime, and gets Alice's basically public key. So Alice's public key, he computes for Alice's public key from decapsulation and compares it with whatever he received. Okay, going back here to the starting point again here, as you could see, EBA calculation is super easy. From EBA you can get J invariant, you can XOR it with C. So basically C is what is coming from that M, PKA, and C, right? Alice is sending ciphertext. Ciphertext includes PKA and C. So up to here there is no difficulties, and then he again performs hash, and then gets EA prime. From EA prime will be the key, will be the public key of Alice, and performs the check to make sure that the public key that he received from Alice is the same as that what he, and if they're the same, basically he is good, and he can perform, he can calculate the shared secret, which is gonna be a shared secret of Kachak of message M, PKA, and C. Okay, similar thing what Alice did for encapsulation up there. She calculated up there for the shared secret. So as you could see, the computations are basically, if we look into that, are basically isogeny computation and evaluation are the main computations that we need to perform. And here are kind of a host CPU, random keys or secret keys are generated here. We push computations to isogeny accelerator, could be in hardware or could be in hardware and software with some kind of soft processors. So data, host CPU sends data request to SIKE. SIKE performs the computations and returns back the whatever needed for key exchange. So hash function could be, or Kachak could be done in hardware accelerator. Sometimes it's faster. We can also push back to host CPU to perform it in software. So if we do in hardware, we can save a lot of clock cycles in terms of the computation. Isogeny accelerator itself could be done using hardware only or hardware software method to perform the make them computations more flexible for various security levels. So one important point is that when I say point, Alice sends the 3 parameters as the public key, or Bob on the other side, they don't send actually the elliptic curve. Basically, they send 3 points on the elliptic curve. So it's XP, XQ, and XP, Q minus P. And since we are working on Montgomery curves, if you've done elliptic curve cryptography, you know that if you know 2 points, x coordinate of 2 points, and difference of these 2 points, you can perform, you can make addition, and you don't need to work on y coordinate. That's why we work on basically x coordinate only on here. Comparing parameters to classical cryptography, I put them in bytes. RSA level 1 is 384 byte, ECC is 32, and SIKE or compressed SIKE is almost about 200 bytes. As you could see, SIKE is even offers a smaller key size than RSA, although it's bigger than ECC, but to have quantum safe security, that's important to keep that. So remember that for the lattice space and code base, we are working on like from 1 up to tens or hundreds of kilobytes. Computation wise, because SIKE performs key generation offline, the computation time for SIKE is basically only encapsulation and decapsulation, which is very good actually. So encapsulation is composed of for NIST level 2, which is 503 prime, P503 means that P is equal to the power of 503, something like that. Okay, the encapsulation only requires, as you could see, 43,127 addition and 64,372 multiplication, and only 3 inversions. So inversions are not that contributing to the cost of computations, and addition is also always cheap. Multiplication is the main determining factor. So if those cryptographic engineers would like to speed up or boost the performance SIKE, I highly recommend to look into multiplication, because it's very tricky, it's very complex, and we have a lot of multiplications to perform. So same thing applies to decapsulation. Decapsulation is more costly, a little bit, like 69,550 actually operations for just multiplication. I compare here a little bit of resource utilization on Xilinx Vertex 7 FPGA. As you could see, just everything is below 20% utilization of Xilinx Vertex 7. I have also detailed of the results in next slides for those who are interested to look into them. For NIST level 1 security, as you could see, if I implement SIKE in ARM Cortex A53, which used to be very popular for phones, these days actually phones got very faster. Even iPhone 12 is coming with ARM Cortex A82. So we computed just in NIST level 1 65 milliseconds. Okay, if we push things to hardware, RTX 7 FPGA with 10 kilo slices, computation time will be about 10 milliseconds. Okay. So, and on the other side, for computations to be done in IoT devices, ARM Cortex M4 computation, this is done with a collaboration with my group and Dr. Hwajung Siu, that we received fastest results for SIKE on ARM Cortex M4 recently, something above 1 second or 1000 milliseconds. And if you push things to a little bit smaller hardware like RTX 7 FPGA with 3 kilo slices, you can perform things in about 200 milliseconds. Still, the gap between hardware and software is not that big, but still 10 times the hardware up could be 10 times faster. So if I push more, I think I could get more, a little bit more. As you could see, 10 kilo slices gives me 10 milliseconds. So here I provide a little bit more details of implementations from round 1. I have here also round 2 results for those who are interested. For example, in Xilinx Vertex 7, the NIST level 5 computations are about 26.9 milliseconds only. And for NIST level 13, recently we reduced the computation time for the SIKE level 1 to about something like 8 milliseconds. So the case for SIKE is a little bit complicated and interesting, attractive actually. So post-quantum landscape is uncharted territory. So the smallest scheme is the slowest and the fastest scheme is the largest. So it means, for example, RSA is requires the biggest key size and offers slowest computations, right? On the other side, ECC is the fastest and also smallest key size. So here things are different. Lattice-based crypto is fastest, but the key size is bigger. Code-based cryptography offers the biggest public key size, smallest ciphertext size. Performance is also fast. SIKE offers fastest key size, slowest key size and faster and very slow computations. So by the time it's getting actually faster, and that we say SIKE's advantages will become more pronounced over time, and SIKE disadvantages will be less pronounced over time. And that's what we would like to see for the computational cost. Computational costs are coming from hardware that we do computations, right? So hardware gets faster over time. So remember, so in 2010 we had iPhone 4, now we have iPhone 12. They're like dramatically different in comparison. Software also gets faster over time, right? Computation in software gets, because of hardware, gets faster, right? The above happens naturally without effort or expenditure. So at that time, even probably iPhone was same price or even same technology, right? I would say sometimes it's getting even cheaper. Technology gets better. And across the board performance increase reduces the performance penalty of SIKE. So if I pay more money into my hardware, I can make my computations faster, right? Certain expenditure, hardware provides good value for per unit cost. But from communication cost, so as hardware and software gets faster, attacks get faster too, right? Attacking NIST level 1 ECC used to be 160. Today 2020 we have like a 256-bit ECC, right? So faster attacks requires a larger key size to counteract. So assuming that you're working with Frodo-Chem lattice-based crypto solution, key size of being 10 kilobyte, and their attacks are getting faster. So what you want to do, you double your key size, right? So 10 kilobyte to 20 kilobyte, or code-based cryptography, 1 megabyte to 2 megabyte key size. So compare with SIKE, the key size is something about 200 bytes. Let's assume that we double the key size to 400 bytes. So you're comparing 400 bytes to 2 megabyte or 20 kilobyte, right? Lattice and code base mainly. Variance in communication channel is much higher than variance in cycle counts. It means I can pay more to get faster computations, right? But I cannot pay more to buy more bandwidth, especially for IoT devices that they're operating in low data rate. So faster computations is not going to contribute your whole cost, because you can't send them fast, because you're working with like something, let's say IoT devices working connected to smart cities, LoRaWAN working 10 kilobit per second, right? They're not 5G. They're not working with like a 100 megabit per second, right? These devices are battery operated, working on high data rate will eat their battery, and they operate kind of with gateways operating in 10 or 20 kilobit per second, something around that. So it means that working in low data rate for IoT devices and communication channel expenses, SIKE wins counterparts, for example, lattice and code-based mechanism. So I stop here, and I would like you enjoyed my talk. I will be happy to answer your questions if you have any questions. Otherwise, thank you very much for having me, and it was my pleasure to speak here. Thank you.